Today we're going to start our study of motion, and specifically we're going to start out by talking about distance, velocity, and acceleration. So the area of physics that we're going to be studying is called mechanics, and that's the area of physics that has to do with motion and forces. And we'll be talking much more about forces in the next PowerPoint, but here we're going to start with the basics of motion. Just to give you a little bit of history about this, Galileo is often called the first scientist, and he was the first person that we know who tried to study motion. And you may have heard that he did experiments such as dropping objects off the Leaning Tower of Pisa in Pisa, Italy, to try to figure out how objects moved. Newton came after Galileo and continued Galileo's work, and he came up with 3 laws of motion, which we'll be talking about in the next PowerPoint. So let's start out with our first concept, which is the concept of velocity. And in this course, we're not really going to distinguish between velocity and speed, so you can think of them as essentially interchangeable. Galileo was the first person to develop this concept, and basically he said that velocity is equal to the distance traveled divided by the time it takes to travel that distance. And certainly this is something that we're familiar with. For example, if you're driving at 50 miles per hour, that simply means that you're traveling a distance of 50 miles in 1 hour. So that would be your velocity. Let's take a look at what we use for units when we're dealing with velocity or speed. One of the ones I've already mentioned is miles per hour. You'll notice, by the way, that we don't write it as mph. And the reason that we don't do that in science is because we use m to represent meters, and so we don't want to confuse that. So if we're writing miles per hour, we'll write it as mi/h. Other units for velocity really can be anything that is a unit of distance over a unit of time. So for example, a kilometer per hour is another common velocity unit that you see on your car speedometer along with miles per hour. The SI unit for velocity is meters per second. So that's the SI unit. And one of the things that you'll notice about that is that that is an example of what we've called a derived unit. Which simply means that it is the combination of 2 base units, meters for distance and seconds for time. Let's take a look at an example. So here we have a problem that says an athlete runs the 50-yard dash in 10 seconds. What was her velocity? I really want you to get in the habit of doing the following, and that is, first, make sure that you write the equation that you're using. Okay, so write the equation. And then show me the numbers that you're plugging in. So in this case, we're taking 50 yards divided by 10 seconds. And then when you write your answer, make sure that you not only write the number, but that you include the units, because without the units, we don't know whether it's right or not. So the answer in this case would be 5 yards per second. Okay, so show the formula. Show the unit or the numbers plugged in. And don't forget the units in your answer. Speaking of units, let's do a quick unit conversion review. I have a car that's moving at 60 miles per hour. How fast is that in meters per second? So we want to start off with 60 miles per hour. And we now want to do what we did previously, which is figure out how do we set up our ratios of our conversions. So let's start out by trying to figure out how to change miles into meters, since we want to end up with meters per second when we get over there. I've got miles on the top and I want meters on the top, so that tells me that my conversion should be meters over miles. So I see that there are 1,609 meters in 1 mile. Okay? And so you'll notice miles now cancels with miles, and I've got meters per hour. Obviously I want meters per second, so I've got to get rid of hours next. And I've got to do that in 2 steps. I have hours over minutes. So there's 60 minutes in 1 hour, and that will cancel out the hours. And then I want to end up with seconds on the bottom, and therefore I need minutes on the top, so they cancel. So minutes cancels with minutes. And you'll notice I now have meters on top and seconds on the bottom. In terms of doing the math, you'll notice I'm taking 60, I'm multiplying it by 1609, I'm dividing by 60 and dividing by 60 again. And we can simplify that. We can cross out those two 60s so that you're taking 1609 and dividing by 60. You will get 26.8 meters per second. And I just wanted to look at that answer for a second. That's kind of interesting. You'll notice that if you're driving down the highway at about 60 miles an hour, what that means is for every second that goes by, you're covering almost 30 meters. Now remember, there's about 3 feet in a meter roughly, so you're going about 90 feet every second, almost 100 feet per second. And that's why when you look down at your radio or your cell phone for a couple seconds, you realize you've gone a couple hundred feet in that time if you're going at 60 miles per hour. And that's why people often get in trouble on the highway, because you're covering such a large distance every second that if you kind of look away or get distracted, you can look up and all of a sudden, somebody's stopped in front of you. All right, so in the example that we've looked at so far, where we had our athlete running the 50-yard dash, we're basically just assuming they were running the same speed or the same velocity the whole time. But obviously, oftentimes things speed up or slow down. And in that case, we can define what we call the average velocity. And the average velocity is simply defined as the final velocity plus the initial velocity divided by 2. So the bar over the V here stands for average, and V final represents the final velocity. V naught represents the initial velocity. And you'll notice that I called that naught. That's how we pronounce that. So that 0, which stands for initial velocity, we call naught. Okay? So to find the average velocity, I take the final velocity, V final, add the initial velocity, V naught, and divide by 2. So let's take a look at an example that illustrates using these two formulas again. So I start out, I have a car travels 600 meters in 25 seconds, and I want to know the velocity. So V is equal to d over t. And I want to show the numbers plugged in. So it travels a distance of 600 meters in a time of 25 seconds. And if you work that out on your calculator, you should get 24 meters per second. So now let's continue. It says if the car now speeds up to a final velocity of 40 meters per second, what was the average velocity of the car? So in other words, we know its initial velocity, V naught, is 24 meters per second. And we know its final velocity is 40 meters per second. And so the average velocity during that time is going to be somewhere in between that. And that's what our average velocity formula allows us to calculate. So the average velocity is just V final plus V initial divided by 2. And that means I take 40 plus 24 and divide by 2. and I get 32 meters per second. And that would be my answer for the average velocity. Let's now talk about acceleration. Galileo also developed this concept of acceleration. And acceleration is equal to the change in velocity divided by how much time went by while the velocity is changing. Now, we all have a sense of what acceleration is. You know that that thing that you step on in your car is called the accelerator. So when you step on the gas, your car speeds up. Well, that means its velocity is changing. So that means you're accelerating. What sometimes we don't think about, though, is that if you step on the brake, your velocity is also changing. So we also call that an acceleration. In everyday speech, we say deceleration, but in physics, we just call either one an acceleration. So if your velocity is changing, you are accelerating. Let's take a look at the formula for this. You'll notice that it's the change in velocity. So that just means I take what was the final velocity and subtract the initial velocity, and that would be the change, and then divide by how much time it took to occur. Notice also that if the velocity is constant, then the acceleration is 0. Because if Vf and V naught are the same, you get 0 in the numerator. So acceleration tells us how the velocity is changing per time. Let's take a look at what the units are of acceleration. Well, we have that acceleration is equal to Vf minus V naught over t. So you'll notice that we have units of velocity, which are meters per second, divided by units of time, which are seconds. And you'll notice that's simply saying that the velocity changes, or the amount the velocity changes, per second, or per time. So if I have an acceleration of 30 meters per second, it would mean that for every second that goes by, the velocity is changing by 30 meters per second. Now, often when you see acceleration units written, it's written this way, as meters per second squared. And I want to show you where that comes from. So I've got meters per second over seconds. But I can deal with units just like I would any fraction. So that would be the same as meters over seconds divided by seconds over 1. And remember what we do when we divide fractions. We take the bottom fraction and we flip it. So I'd have 1 over seconds. So meters times 1 is just meters. Seconds times seconds is seconds squared. So meters per second squared is the way we usually say the units for acceleration. But it's important to understand that really what we're saying is meters per second, the amount the velocity changes per time. So let's take a look at an example. A car accelerates from 0 meters per second to 50 meters per second in 10 seconds. What was the acceleration? So again, I'm going to write down my formula. The acceleration equals Vf minus V naught divided by t. And in this case, the final velocity was 50. The initial velocity was 0. And it took 10 seconds for that to happen. So I get 50 divided by 10, which is 5 meters per second, or 5 meters per second squared. Now, I want to just show you exactly what does that mean to have an acceleration of 5 meters per second. And I want to just kind of show you this by making a little table for the time and for the velocity. So when we started out at 0 seconds, the car wasn't moving at all. And the question is, how fast was it going after 1 second? Well, if we are accelerating at 5 meters per second for every second, that simply means we're gaining 5 meters per second of velocity for each second. So in other words, after 1 second, we're going 5 meters per second. After 2 seconds, we've gained another 5 meters per second of velocity. So we'd have a total of 10 meters per second. After 3 seconds, we've gained another 5 meters per second. So we'd be at 15. And I'll just keep going here. After 4 seconds, we'd have gained another 5 meters per second. So we'd be at 20. And just keep going here. So after 7 seconds, we'd be going 35. After 8 seconds, 40. 9 seconds, 45. And finally, after 10 seconds, we'd be going 50 meters per second. Well, that makes sense because that's, after all, what we started out knowing. So acceleration just tells you how much the velocity is changing in every second. Okay, so every second that goes by, the velocity changes by that amount.